Welcome back to another video lecture in preparation for a lab. The lab that this video will prepare you for is the lab on grapheme to phoneme tools. At least one, you choose which one. And so let's look at some slides here. Jump over to here, go like this, this, and this. So what we have here is grapheme to phoneme conversion, and I will tell you what graphemes are and phonemes are if you don't already know. So let's talk about the languages of the world and the sounds of the world. As we saw in a previous lecture, there are over 7,000 languages according to Ethnologue, I believe it is, and many more dialects of those languages, right? There's one English language, but many different dialects or varieties of English. Sound segments, aka phones or individual sounds, we've talked about that, right? So we have p and g and h and b and r or whatever. And there's a relatively small set of possibilities that's limited by human anatomy. Okay, and just to review, we talked about vowels and consonants, I believe. Vowels have no substantial constriction of the airflow from the lungs out of the mouth, the body, either through the mouth and or nose. And there are many vowels. Well, it depends on the language, right? There could be up to 64 vowels in some languages, or as few as 3 vowels in other languages. English has 12 or 13, depending on the variety that you're thinking of. Consonants, there's some kind of substantial constriction of the airflow with consonants. And there can be as few as 8 consonants in some languages, or as many as 98 consonants. And then a third category or class of phones or segments or sounds are glides, and they're kind of halfway between a vowel and a consonant, like y and w, where they're not quite fully vowels, they're not quite consonants, they're called glides. And speech processing deals with phones and diphones and triphones, that is 2 phones together or 3 phones together, right? Diphones and triphones. And just to review, syllables are a coherent structure of associated sounds in the speech stream. And the phoneme is what is, I like to refer to it as a family of sounds. So it's a combined, like contextual variants of a basic sound in a language. So for example, the phoneme L in English has 2 variants. The phoneme T in English has as many as 8 variants. The phoneme B in Spanish has at least 2 variants. And those variants are what are called allophones in technical linguistic terminology. Just to review real quick, phonetics is the science of describing and inventorying the features and structure of the basic sounds of speech in different languages. And there are 2 main branches: articulatory, deals with the body parts, and acoustic, which deals with sound waves. So let's talk about orthographies, the writing system of languages, right? In English, we have an alphabetic writing system, which is roughly 1 symbol per sound. That's also the case with Armenian, which uses a different writing system, different script. You can have some orthographies that are based on syllables or syllabic, where there's 1 symbol per syllable, like in hiragana in Japanese or Cherokee. Or you can have some writing systems that are based on a consonant vowel or a CV structure, like in Thai and Tibetan and others. Or you can have a logographic, like we mentioned, where it's roughly 1 symbol per word or idea, like Chinese and Egyptian. Or you can have some writing systems that basically just have the consonants and have omitted all or some vowels, like Arabic and Hebrew and Persian. And so the word grapheme is a technical linguistic term that means a symbol or character. And there's wide variation in how closely the orthography reflects the pronunciation, like I mentioned. You can have what is sometimes called a deep orthography. We have a wide difference between written and spoken language. So looking at these words in English, here at the bottom, we have tough, though, through, bow, cough, thorough, right? And so they all end in the same 4 graphemes, but the pronunciation varies. And you can even get, some orthographies like this, like hiccup, Less commonly, hiccup can be spelled like that, apparently, right? You can have this kind of silly orthography, or this silly writing of potato. Potato coming from, let me zoom in a bit, right? The GH of hiccup, P, the OUGH of though, and the P of this word, right? Which actually is just a T, that P is silent. Anyway, so they, as a funny thing to do, they've spelled out potato using these graphemes based on these other words in the language that have those sounds. Okay. And so English has a relatively deep orthography. That is, there's kind of quite a big difference between the written form and the spoken form. French is less so, but still pretty distant with these scores that linguists have ranked the distance between the orthography and the pronunciation. They can give it a numeric score here. Some orthographies are very shallow. That is, there's very little difference between the orthography and the pronunciation. So Finnish is like nearly a one-to-one match, or if I don't know Finnish personally, but it receives a score of 0.0, whereas Hungarian is very close as well. Like I mentioned before, Spanish is pretty close as well. I don't have a score for Spanish, but you get the idea that some orthographies are closer or more distant from their pronunciation. Danish is also pretty distant, pretty deep orthography, I think, from what I've learned about Danish. So speech processing uses both phonetics and orthography. So we have to be able to convert from orthography to pronunciation or vice versa, right? And hence the idea of grapheme to phoneme conversion, or sound to phoneme to grapheme conversion. So one approach, there's several approaches here. You can standardize all sounds in all languages with one representation. You can standardize phonetic alphabets for use in speech processing, for example, like the IPA. Develop tools to automatically look up transcriptions, like in a dictionary, like a pre-made resource, like a dictionary or a lexicon. But there's always a problem of out-of-vocabulary words. That is, words like, especially proper nouns, that are not in some dictionary or lexicon that was already previously created. So that's always a problem. So how you deal with out-of-vocabulary words is important. Another approach is develop tools that can automatically convert between representations based on knowledge and machine learning techniques. So just to review real quick, the International Phonetic Alphabet is a set of symbols used by linguists to represent sounds, right, regardless of the writing orthography system, just the sounds themselves. And it's based on articulatory features. So across the top here, the columns are places of articulation in the mouth and the throat, right? The bilabial is two lips, labial dental is lips and teeth, the upper teeth and the lower lips, for example, like in F. Dental, the teeth, right? Velar is the soft palate in the back, the velum. And then on the horizontal or the vertical, the rows here are manners of articulation. So plosives have a full stop and then a release where there's like a slight explosion or a slight, pop of air. Plosives, nasals, there's some air coming out of the nose, right? So that's how that International Phonetic Alphabet is set up like that. And then on the left and right of each cell, you can see the voicing of the vocal folds. With P, there's no voicing. With B, there is voicing. Okay. This is great for linguistics, but not super practical for speech tools. And this International Phonetic Alphabet is often used for annotation in Pratt text grids, where people are listening to sounds and marking with these symbols what sounds they're hearing. Okay, but there are other phonetic alphabets out there that have been proposed, that have been used and are in use. ARPA, developed by the U.S. Advanced Research Projects Administration, is what that stands for, is ARPABET, is this set of kind of ASCII-friendly characters to represent different sounds. So the IY there, this ARPABET character grapheme symbol, represents this vowel in here, beat, whereas the IH represents bit, a little bit lower lax vowel, E versus I, I, right? So those are represented by two symbols here. Okay, so that's ARPAbet. Current name is DARPA for defense. Okay, another phonetic alphabet is the Timet bet and the OGI bet. Here's examples. You can see again that we have examples in English, standard orthography, and what the Timet bet symbol is here. Another one, world bet, kind of the same idea, where it's different conventions that are used to represent the same sounds that we've seen with others. Samba, that is, not samba, but Sampa is used mostly in Europe. Was created, I believe, in collaboration, European Community Languages. These there in 1989, a couple more in 92, etc., and some more and more. Anyway, so this is used more in Europe than the U.S. In the U.S., ARPAbet is often the one that's the alphabet that's used most. Okay, the CMU dictionary, the CMU pronunciation dictionary. CMU stands for Carnegie Mellon University Dictionary. For short, is a pronunciation dictionary where you have orthographic representations and graphemes, and then you have ARPAbet symbols that give you the way the word is pronounced. And if there's more than one way that a word can be pronounced or is pronounced, then there'll be more than one entry. So representative, let's see, representative versus representative versus representative. Anyway, these are ARPAbet symbols here, and the numbers that are on the right side of the vowels indicate the stress. Whether you have 0, that is no stress, like it's fully unstressed. Number 1 is a primary stress, and number 2 is a secondary stress. So if we look here, this EH1 means that vowel is the stress vowel in this articulation of representative. So zentative is the one that's has primary stress. This one that's secondary is the first one, representative. So anyway, Gerald Lonsdale in our department was a student at Carnegie Mellon University when this was being created, and so he added his name with its proper pronunciation. You can take a look, you can download it on the link there. This is on a GitHub. You can come in here, and if I just click on cmudict.dict, which stands for dictionary, you can look at it. It's just a text file with all the words and all of their ARPAbet pronunciations. Let me zoom in. There we go. A bit more there. Okay, there we go. So look at all these words in English. Abbreviation. There's one there. Anyway, you can see there's a truckload. I don't know how many words there are in here, but a lot. Rituals. Okay. There's an online lookup if you want to just use an online interface to look up something real quick. Like if I were to type in, I don't know, book, you can see that there it is right there, book. If you want to show the stress, if I type in university and let it go, you can see that there's university, and it did say, hey, verse has primary stress, university. Okay, let's take some time to look at that. The CELEX is another lexical resource that's really useful, has information about phonology. Obviously, the orthography is standard orthography, but also phonology, morphology, and syntax. And this is a resource that I mentioned is available through the Linguistic Data Consortium at the University of Pennsylvania, that you have to have subscribed to it, and we at BYU have, and so we have access to this resource. Here's an entry for basketball. You can see that they have this representation in phonology. And then they have like a syllable structure, consonant and a long vowel, ba, and then sk, it. So consonant, consonant, vowel, consonant, sk, it, right? And then ball back there as well. So different approaches to doing G2p, G2p being short for grapheme to phoneme conversion. You can just have a dictionary lookup table or list, right? It's kind of like what I just showed you with the Carnegie Mellon University dictionary. Or if you want to look up dog, we would get this. Oops. we would get this entry right here, or like in CELEX as well, or the Oxford English Dictionary. If you look it up, you can get pronunciations in there, right? This is very fast. That's a positive thing, but it's very difficult and time consuming to actually create these. And again, it's like a never ending task because there's always new words and proper nouns that aren't listed. There's always these OOV, which is out of vocabulary words, and there are disfluencies that aren't listed, right? So it's fast, but difficult to create and maintain, and really an impossible task to know beforehand what words you're actually going to need, right? Those out of vocabulary words are always there. Another approach is to create what's called a finite state automata or automaton. Singular, automata is a plural. And this is very fast and generalizable, but the con is it needs some training data. Or a third approach is to do machine learning, including neural networks. The positive thing is that it's generalizable, but it also, a negative is that it needs vast training resources and can be very slow, especially neural network. So finite state machines, or finite state automata, plural, are systems that contain a finite set of states. You have an initial state and then a final state. They're often numbered, like in the bottom left of this screen, these different states. And they have a finite set of symbols or labels, like an alphabet or an IPA symbol or an ARPABET symbol. And then you have a finite set of transitions from state, by symbol. So they're fairly easy to implement, and they represent a network. You can represent them as a table on the bottom right of this screen. So to go from state 1 to state 2, you pass through A and have A, and you can go from state 2 to state 3 by going through big, dog, yawned. So this can be represented in a table as well, like this, from one state to the next, like that. So that's just a quick rundown of a finite state machine. Let's take look at it some more. So a finite state transducer is a way to translate or transduce or change from one state to another. So for example, let's say we have Christmas. This right here is Christmas. So at the beginning, we have on the left-hand side of each colon in each pair of symbols here, we have the orthography. So this is the beginning of the utterance. Here's a capital C, H, R, I, S, T, M, A, S, and then end, final state, pause, or the end of that state, right? And we go from each of those into some phonetic representation. So K, and then the H is not pronounced as an H, it's just not there. Then an R, and then an I, and then S, and then the T is not really pronounced. Christmas, we don't really say the T right. We don't say Christmas, say Christmas. And then we have schwa back here, and then S. So the idea is with the finite state transducer, that the overarching global idea is that you're going from one representation to another. This can apply to many different fields, not just linguistics, not just speech processing. That's the main idea, is that we go from one state or one representation to another. And each state is a transition with an input and output symbol, and those are a pair. And it allows for changing input sequences into output sequences. So for example, going from orthography over to the International Phonetic Alphabet, or vice versa. So these finite state machines have many useful properties. You can do set union and concatenation and intersection and other kind of set operations on them. And they become very flexible and represent most of what we need for grapheme to phoneme, or g2p. And like I mentioned, they're used in many other fields besides linguistics. They're very efficient computationally. And there's lots of different toolkits to support development of finite state machines and transducers. And there's some that are specialized that have been developed just for linguistics. And there are others that are just general that can be used for linguistics or other things as well. And so some special characters, a plus sign is like a morpheme boundary, a hashtag or a pound sign or number sign is a word boundary, a asterisk is a wildcard, and 0 is a null character. Like we saw previously with Christmas, the H is not pronounced, the T is not pronounced, and so there was zeros. Let me just go back one slide real quick. Yeah, see right there, zeros right there for those two input things that shouldn't be represented in the output. Special symbols, well, we have V for vowel and CN for consonant, NAS for nasal, and other kind of special symbols that are used. So a finite state approach, so there are two level rules here. We have orthographic representation and a phonetic context as two separate layers. So on the top here, the L, let's call this the lexical level here, perhaps like even the underlying level. We have APNA, where we have AP and then a morpheme boundary, and then an MA. And that would turn into a surface level, or like actual pronunciation of ABNA, where that P turns into a B in a certain context. And that context is written out in a rule. You can define rules for mediating between the input layer and the output layer. In this case, the lexical layer and what's pronounced. So a P turns into a B in the context of right before a morpheme boundary, which the morpheme boundary is lost right before an M. So that's the way you'd write out a rule in a finite state system, finite state transducer system, to turn a P into a B right before a morpheme boundary and right before an M. Okay. But if P, a second option is to not change, right? So it's not a categorical rule. But if there's not an M, if it's like a B that follows, then that P stays as a P. Anyway, so the idea here is that you can create rules to go from the input layer to the output layer. And then you compile the rules into an engine that does the computation. And so the task, the lab that you will do for Grapheme to Phoneme, you'll pick one of these tools that I have a list of on a slide or two, and get to know how to use that tool. And this idea of a finite state machine is widely used in speech technology to convert between graphemes and phonemes and vice versa. So here's some examples. Here's an example from Russian. Let me back up. That the past tense L, right, is lost in this context. L is lost. In this context. And here's another example from language that Dr. Lonsdale studies Lachute seed in the northwest US and the southwest Canada. This U is lost, turns into 0 before a morpheme boundary. Okay. So here's a list of some of the finite state tools for transcription, going from kind of easier to harder, going down the list. Okay, so your task for the lab is to choose one of these and learn how to use it. Try your best to learn how to use it. So here is one. This is just called g2p, and it is a grapheme to phoneme transformation that preserve input and output indexes. This library is for handling arbitrary conversions between input and output segments while preserving indexes. Anyway, it's a good tutorial, and there is a 7-part series on a blog that walks through it. Here's a more technical paper. Excuse me. Phoneme is another kind of easier system. I'll let you look through these. You will need to choose one of these. OpenFST, finite state transducer, is a little more advanced. But anyway, I'll let you look through those. And part of the preparation is to actually look through this list here and kind of click through each of those and see which one you might want to use for your lab. Okay, machine learning is another way to approach converting from graphemes to phonemes and vice versa. And so you obtain a large number of G to P correspondences, that is grapheme to phoneme, right? For example, a corpora transcribed at the phoneme level, for example, would be like the training data. You use that to train a computer to recognize the best alignments and the best configuration of graphemes to phonemes based on the data, based on what it sees in the training data. And there are several different algorithms or approaches to doing that. And then you present new input into a system and have it analyze and generate rules, right? That's what machine learning is. There are many different systems and toolkits and ways to evaluate it. Here are some examples in the bottom right. Some English mixing, right? Go from this M to M, lowercase I to uppercase I, that is I. This orthographic X to kus, and then this ing to just or I, or it's a velar nasal. Here's some examples from other languages, Mongolian and others. So other tools for transcription, NLTK, Natural Language Toolkit, and Python. There are other Python tools. There's a seek to seek or sec to sec machine learning approach. And there's neural machine learning approach. This right here, this polyglot, take a quick look at it. It is a tool here, polyglot. It's a natural language pipeline that supports massive multilingual applications, right? Not just transliteration and all sorts of stuff that it can do. Oops, I just wanted to, or speech tagging as well. And it's a natural language processing toolkit that has transliteration, word embeddings as well, morphology, transliteration between languages, which can be useful. There's another one there. So, well, how well does it work? Well, it's not perfect, but it is useful, and it is state of the art, the best that we can do right now. Surprisingly, neural networks are not quite as accurate as finite state transducers, but a hybrid system where it combines neural network machine learning as well as finite state transducers are currently doing the best. And it varies across languages, obviously, how accurate a grapheme to phoneme conversion is. And obviously having a graphical processing unit, a GPU on your computer, helps speed up the time here. The top right, this comes from the paper, the technical paper. Let me just go back a couple slides. Where is it? I think it's this technical paper. That image comes from this paper written by a bunch of people. But they're talking about this architecture, this g2p studio, and they have this was not the paper I was thinking of, sorry. One of the papers has this time, this benchmark about the speed. So you can see that the neural network based using GPUs is quickest, the bottom line there. Okay. So yeah, the next lab is to get to know a g2p tool, a grapheme to phoneme tool. You become familiar with it, with the various phonetic alphabets representing English, right? And work with one or more of the g2p systems. If you just choose one and get to know it really well, that's totally fine. You don't need to feel the need to learn more than one if you don't want to. Okay, so install, write knowledge-based sources like rules for a few several phonological transcriptions in some language, for example, English. Compile them into an engine using the software. Run the engine on some text. Evaluate the output. How well does it do? What issues? What problems? Repeat as necessary. Repeat and revise and add rules to get to know how it works. Then you write up. You write up what you did and what your code, some of your code, like some of your rules, and some of the input and output that you put into the system. Okay. So yeah, grapheme to phoneme is a very important part for speech processing and speech synthesis. See you in the lab.